Welcome back. This is an Aleks homework video on understanding the qualitative predictions of the Arrhenius equation. Okay, this looks so mathy and hard, but really if you can simply write down this equation, you can get a lot of information from it. So essentially it's going to find out what is happening to the rate of a reaction if you know the activation energy or if you know the temperature. Okay, so as the temperature goes up and down, what happens to the rate? Okay, so you know that you would use a Bunsen burner in a chem lab to heat the reaction so that the molecules bump into each other more. Okay, so heating it has a lot to do with how fast it's going to react, or slowing it down. You put something in the refrigerator so that the chemical reaction of spoiling doesn't happen. Okay, or you put something in the freezer so that it doesn't spoil. So you know that temperature has to do with the rate. This tells you how it does it. Also, the activation energy of the reaction also will tell you, if you know the activation energy, how much energy is required to make these molecules rearrange themselves. If you know that, you can also know what's going on with the rate. So it's extremely useful. I'd hate to have derived this myself. I'm not smart enough, but somebody is. I guess Mr. Arrhenius is. And once you know it, you can use it. All right. On the right, I have got two graphs that Aleks gave you that really does help you. Okay. So let's look at one at a time. Let's do the one on the bottom first. So this is temperature. As the temperature goes up, okay, as the temperature goes up, say from 300 to 350 or from 350 to 400, as the temperature goes up, what's going to happen to the rate? Okay, well, the rate is going to go up as well, but they're not going up linearly. If I went up and for every one I went up, it went up one, I'd have a nice straight line. A linear line means that if I go up 10%, it's going to go up 10%. Or if I go down 10%, it'll go down 10%. But if I have an exponential line, if I have a J-curve line like this, if I go up 5% or 10% or 20%, it's going to go up more. So the temperature, since it's exponential, if it goes up 10%, your rate will go up more than 10%. But they will both go up and down together. So if you drop the temperature 5%, it's going to drop, the rate will drop more than 5%. Okay, I hope that made some sense. Because it's not linear curve, the relationship is exponential. They'll go up and down together, but the rate will go up more than the temperature will. Okay, now you have a converse graph on the top. So if you increase the activation energy, it makes it harder to happen because more energy is required in order to make those bonds form or break. And if you increase the activation energy, you're dropping the rate. Okay, so they're inverted. And it's also exponential, which means if you go up a little bit with the activation energy, you go down a lot with the rate. So what does that mean? If you increase the activation energy by 10%, you're going to go down, the rate will go down by more than 10%. If you drop the activation energy by 10%, the rate will increase by more than 10%. Okay, so now that you have that, we can answer the question that we have. All right, so the question that we have says, the temperature is being raised by 10%. Okay? Well, I know if the temperature is being raised by 10%, then it'll rise more than 10%. Okay? So this is going to rise more than 10%. Okay? Because it's exponent. This says that the activation energy is being lowered. All right, so if the activation energy is being lowered here by 10%, then what's going to happen? Well, If it lowers by more than 10%, then the rate is actually going to go up by more than 10%. Okay, so this is going to rise more than 10%. Okay, I hope that helps.